to remind a few things that I've said in the beginning. One is that every participant is supposed to take a folder with his name written on it. So let's do it, because inside there should be some tickets to get your meal. For those who have to pay for the registration and for the tickets, please go to the Géraldine if you haven't done so. Haven't yet done so. So it's Géraldine Arachal, and her office is number 123 on the first floor of the Institute. Another thing you probably got a form for the evaluation of the school. So some people have filled it in, some haven't. So please do that if you wish. And then what else? I think it's all. Oh yeah. Please feel free to use the library. There is also a section devoted to the summer school. So I've noticed that not many people go inside the library, but maybe for the conference part, it's probably important to remind that the library is available for all participants. Okay, so now let me introduce our first speaker today, who is Hiroshi Iritani from the University of Kyoto, who is going to speak about quantum cohomology and theory.
Thank you. Sorry, maybe. I'm sorry, I just have broken the.
It is actually not a microphone, so you should not expect it to repeat too loud. It's just for recording what you're saying.
So I just, I'm broken.
Yeah,
I have
we're
broken something.
broadcasting to the next, but now we're in 20, so we can actually have just a lecture folder. Okay, so obviously you can take this 2 minutes.
Okay, thank you. Thank you. So thank you for the introduction, and thank you for inviting me to this conference. And I'd like to talk about quantum cohomology and periods. This is this very classical topic about mirror symmetry, some classical and also well known. But with some motivation, with some application in mind. And this is based on, the main result is based on the paper, the archive. So this is somehow the relationship between quantum cohomology and periods are somehow very classical subject. And mirror symmetry is all about at least genus 0. Mirror symmetry is all about quantum cohomology and periods. And somehow I'd like to make somehow slightly more precise relationship between quantum cohomology and periods. And actually somehow I'd like to advertise not only somehow the result itself, but also some motivation motivation why I consider the relationship between quantum cohomology and periods. And so the motivation is somehow I'd like to consider I have is somehow to study the analytic continuation of Gromfittian theory. And I think in this week many people will talk about this topic. And so maybe I'd like to pick up some of the subject which should be closely related to this. So of course, from the start of quantum cohomology and mirror symmetry, I think physicists have studied this kind of thing and very precisely. somehow Gromitian theory is, well, somehow it is a collection of various numbers, rational numbers, collection of rational numbers for given degree and some given initial, some given boundary, some conditions. But somehow one can consider actually some potential function. So maybe you can say Gromitian potential. Analytic some Gromitian potential, which is a generating function of such rational invariants. And from physics point of view, Gromitian potential should be somehow analytically continued to certain global function. And then Gromitian invariants are just some Taylor coefficient or Fourier coefficient of some global function. And somehow many physicists have studied this kind of things. So somehow it should be closely related to physics. And another thing I would like to mention is something called Ruan-Yonville-Wans conjecture. Which is also could be referred to as Crepant resolution conjecture. Or Crepant, I don't know, flop conjecture. And so this says that if you have, for example, in the case of Crepant resolution conjecture, if you have Crepant resolution of a certain Gorenstein overfold, so I use this letter curly x to denote overfold. And if y is in Crepant resolution, so that means somehow it is proper birational morphism and pi. So more precisely, this should be thought about a coarse moduli space, but the canonical bundle pull backs to the canonical bundle. In this case, it is conjectured by Ruan that the quantum cohomology of y and quantum cohomology of x are analytically continued. So, or maybe in Fujin's. The Gromitian theory of y and Gromitian theory of x are analytically continued. Analytically continues to each other. And also similar thing should also happen for flop or other rational transformation which preserves somehow the canonical class. And I think this would be explained in White His talk, I think. And perhaps should be related to Cavalieri's talk, perhaps. Yeah, so somehow this is very surprising thing that Gromitian theory originally is just some collection of rational numbers and just make a certain generating function, but it can analytically continue to give something different varieties. Gromitian theory, something different varieties. And another somehow new version of Ruan's conjecture about analytic continuation of Gromitian theory. So if you have, I have a certain Calabi-Yau hypersurface, in, for example, weighted projective space. This is some Calabi-Yau geometry, and this should correspond to certain Landau-Ginzburg model and the Ring pool. obifold. So this is just a physics notation, but Van-der-Gesing obifold for mathematics, it means just a function on some Cn or something with some group action. And then here again, so if you consider the Gromfittian theory for Calabi-Yau hypersurface X, so Gromfittian theory, this side is analytically continued to give certain FJ-RW theory. Some another Gromfittian type theory, which is called Van Jarvis-Gromfittian theory. Which is also a very surprising thing that somehow this is again analytic continuation. Right. This sign is analytic continuation. So analytical Gromfittian theory for Calabi-Yau hypersurface is some analytically continued to certain another theory which is associated to some function on the affine space. So this is some function on the polynomial function on the affine space. And actually somehow this is defined in terms of moduli space of curves, or moduli space of spin curves, or moduli space of W curves in general. And so somehow it is very interesting to study the analytic continuation of Gromfittian theory. Yeah, for example, in this not usable Calabi-Yau correspondence, for example, recent results by Kyoto and Ruan, which will be explained in later talk by Kyoto and Ruan. And so this is somehow for quintic hypersurface genus 0. This conjecture somehow this is somehow analytic continuation Gromfittian potential to FJ-RW potential is proved in his paper, in their paper. And also recent paper by Kravitz, Shen, and also Ilonov-Ruan discussed some higher genus correspondence of Gromfittian theory of, here in this case, I think, elliptic obifold. So elliptic P1 obifold. So elliptic P1 obifold is some P1 obifold with some obifold singularity such that the obifold Euler number is 0. There are finitely many such things. And so this is for all genera. I think these things will be explained in later talks. And also somehow the Ilonov-Ruan showed some modularity of the quasi-modularity of the generating function. So it's very interesting thing to study analytic continuation of theory. Somehow, my topic is about mirror symmetry, some very classical mirror symmetry. And somehow, I hope that at least somehow, in order to prove these things, mirror symmetry is used, actually. And so mirror symmetry is somehow, on the mirror side, you have more global object. On the Gromfittian side, you can get just infinitesimal object, which is just formal function. But on the mirror side, you have some actually global object. So mirror symmetry will help us to understand these kind of things. Yeah. So let me just review what is mirror symmetry. And mirror symmetry, you have Calabi-Yau manifold. Manifold X. Then Calabi-Yau manifold X is mirrored to certain I consider symplectic geometry on X side, and then complex geometry arises usually as a family. So you have a family of Calabi-Yau manifolds, a manifold of the, let's say, same dimension. And so, for example, I consider quantum cohomology of Graham-Witten theory on this side and period on this side. Then, for example, the classical mirror symmetry or topological mirror symmetry says that the Hodge number Pp part of X is equal isomorphic to the n minus p part of Y. This is just isomorphism of vector space. So I just say this is a same dimension, vector space of the same dimension. And actually, somehow more is true. So you can consider somehow this as a Hodge structure, and similarly, you can also consider this as being a Hodge structure. So, and also variation, more of a variation of Hodge structures. And so I just continue the comparison. And on the Y side, I have this n-dimensional cohomology group. Either dimensional cohomology group will split into the direct sum of n minus p of YU. It's the Hodge decomposition. And somehow this is called the variation of Hodge structure because this space does not depend on U, but this decomposition itself depends on U. So, and this Hodge decomposition depends on the complex moduli space parameter U. So this is somehow variation of Hodge structure. And similarly, you have somehow this could be viewed as certain kind of variation of Hodge structures. But now what varies is not U, but what varies on X side is scalar parameter. So I have some called quantum cohomology, and which is this is something defined by the genus zero Graham-Witten theory, quantum cohomology, which is parameterized, let's say, parameterized by H2 of X, or maybe more precisely H11, compatible with this. But let us assume that H11 is equal to H2. And so this is some family of rings parameterized by a point on H2. And this defines defines variation Hodge structure VHS. Okay. And basically somehow the Hodge filtration is given by somehow just n minus pp going to pp. This correspondence defines Hodge structure, Hodge filtration on this vector space. And I need to define certain Gauss-Manning connection, which somehow is compatible with the Gauss-Manning connection on this side. And then the mirror symmetry said that they are isomorphic. And in practice, what we can say is so one can construct certain J function, something called the J function from here. Which is certain cohomology valued function, and some of which is an analog of the period here. So let me take omega u to be a holomorphic N0 form on YU. And then one can consider a period, which which is integration over some cycle of omega u, where C is some n-dimensional cycle. So for each cycle, so this is some hollow n form which exists because yu is Calabi-Yau. And I can consider this thing. So this is called the period. Maybe let me note by pi c of u. This is a function in u and also somehow depends on the choice of a cycle here. Actually, somehow, sorry, I should first explain this side. But the J function, which is defined by Giventhal, is actually an analogy of this period of this quantum cohomology variation Hutch structure. So, so somehow, but the important point for our motivation is that this side, it is a global thing. So this is global function. If, for example, the moduli space is global moduli space you have, then I have some certain global function, could be multi-valued, but some global function. But this J function, which you can define from quantum cohomology, is only infinitesimal thing. And the J function, I forgot to say, but J function is a cohomology valued function. Some function taking values in cohomology. So so the mirror theorem proved by Giventhal and also Yao and also many others states the following. So for a class of X, for example, X is a toric complete intersection. For example, X is toric complete intersection. For X to be a toric complete intersection, in this case, they prove that the J function is equal to some rescaling of some certain another function, I function, under certain change of variables between t and u. So here, t here is a parameter of H11. That means a parameter for the complexified Kähler moduli, Kähler class. And u is a complex moduli space of Y. And so they're under mirror symmetry, T and U are identified, certain change of variables. And where this I is a hypergeometric solution to the Picard-Fuchs equation. Of the mirror. So yeah, yes.
It's only for threefold, right? Otherwise, the J function, the parameter J function is bigger. The T generally will even much larger than H2.
I just restrict to H2. The T is. Yeah. So, sorry, I forgot to explain what the Picard-Fuchs equation somehow is defined by in terms of the mirror complex manifold. It is somehow linear partial differential equation satisfied by this period. So you can think of I to be a kind of analog of the period, and that is equal to J. And this Fu is a rescaling of holomorphic volume form omega u. So omega u somehow is rescaled by F. It is some scalar value function. rescaled by this, because you can always rescale omega u by some function. And so somehow this is a your theorem given tau. So somehow this says somehow J function is some period. At least some component of J function is a period. But somehow I would like to consider a slightly more explicit question that well, the goal of my talk is to find slightly more explicit relationship between J function and the period. So find an explicit relationship between J, T, and period. Of the mirror. So from this one can say that some component of the J function, so at least we can know that the component of the J function, J beta of T, it is, maybe I should write in a slightly different way. So rescaled period, some period, for example, over C alpha, omega u. This is certain linear combination of components of J function, J beta of T. So where A alpha beta is some constant, some linear constant, some given those, and Liu-Yu's theorem, mirror theorem, implies that this kind of equality, but somehow they do not give us somehow the explicit constant A alpha beta. What would be the kind of constant here? And somehow this gives us an information of what is the integral cycle in terms of Bromwhitten theory. So so on this side, you can find some integral. What is the integral cycle? So there is a notion of integral cycle, but we don't know what is the integral component of J function. And so somehow this information gives us certain integral Z structure in on quantum cohomology variation Hodge structure. Z structure on the quantum cohomology variation Hodge. And actually somehow gives us certain polarized variation Hodge structure because of this Z structure, which comes from the mirror. So maybe let me explain some well-known example of mirror theorem. Yes.
By the way, this theta plus rate
Yeah.
generally will have one order higher than the dimension of the space, right? So this does not really imply I function is period.
Right. Somehow that is a more subtle point, but you are right. Yes. But yeah, let me just, for the sake of exposition, just pretend. And yeah, so somehow some very basic example, some of which is well known to the people in mirror symmetry, is a quintic example, where you have X is a quintic threefold in P4. Quintic. This is some Calabi-Yau manifold, and YU, in this case, YU is given by certain Calabi-Yau compactification. This is known as, for example, Batilev mirror or Green-Presser mirror. of the following affine variety. The mirror of a quintic threefold in X is given by this very explicit equation. Somehow this equation comes from the data of a fun of P4. And the Newton polytope of the, for example, this equation is a fun polytope for P4. So somehow you can do this for whatever reflexive toric variety, a Gorenstein toric variety. And there, but we have shown that there exists some Calabi-Yau compactification of this variety. And one can somehow take omega u to be certain residual form dWu. So where W is a defining equation of this variety, W. This extends to, this is a holomorphic three-form before compactification, but it extends to the compactification to give you some nowhere vanishing three-form. And Picard-Fuchs equation in this case is somehow also well known, but just remind you. So this has satisfied the following fourth order differential equation: 5u 5 theta plus 1, 5 theta plus 2, 5 theta plus 3, 5 theta plus 4 of the integral of u is equal to 0. So for any cycle, this differential equation, you can actually check very elementary that this equation is satisfied. And then you solve the differential equation. Now solve the differential equation. To get the I function. Thank you. Yes, I forgot to say. Here is u d by dt. Thank you. And somehow, to get I function, you just solve this differential equation by a standard method, or Frobenius method, and then you can make it some cohomology values function, and then one can know the J function. There is some method to determine the coordinate change and also the scalar function fu, but I don't explain. But okay. So somehow this mirror construction is, for example, generalized for toric variety by Batilev, and also a complete intersection in toric variety by Batilev and Borisov. So So now I'd like to somehow explain certain Z structure. Somehow I can extract the Z integral component of the J function. Z structure defined by the K group K of X. So assume for simplicity that the dimension of H2 of X is 1. I don't need this assumption, essentially, but just for the sake of exposition. And in this case, the quantum product the quantum cohomology is certain associative commutative algebra, actually supercommutative algebra, but it is somehow the deformation of the cup product. So the first order, 0th order, it is cup product plus certain correction from some higher degree curves. And I have some, I don't explain this part, but u to the d, where this box is defined by counting genus zero curves in X. And also Q is exponential of t, because now H2 is one-dimensional, so t is in just one variable. So somehow quantum product is always of this form, and when Q, if you set Q to be 0, then this is a cup product. And associated to it, one can consider a certain Robin connection called quantum connection. So this is mirror to the Gauss-Manning connection of the mirror. Robin connection. Let phi be a basis of H2 of X. So now I'm assuming H is a one-dimensional. So I pick up one basis, and then T is a dual coordinate with respect to certain basis. This is basis. Take some basis. And then I can write the quantum connection as Q dd by Q plus quantum multiplication by phi. So this is some flat connection on the vector bundle. The following trivial vector bundle so some vector bundle with base coordinate q, and the fiber is just cohomology group. It is just trivial vector bundle, and somehow the first term is just differentiate whatever section you have. You can differentiate in q direction trivially in an obvious way, and then you also quantum multiply by the basis p. This is certain flat connection on the vector bundle, and somehow this is a mirror to, this should be considered to be the mirror of the Gauss-Manning connection. This is somehow mirror of the Gauss-Manning connection. Connection on the cohomology bundle. So so somehow in A model language, somehow quantum cohomology language, there's some given trivialization, but the given trivialization is not flat with respect to the Gauss-Manning connection. Then then I can trivialize, and somehow this is flat in general dimension, but now I'm assuming the basis dimension 1. This is the flatness of the connection is trivial, but in general, you have, even if you have R dimensional base, it is flat. It is known to be flat. So I trivialize this flat vector bundle, the flat bundle over the universal cover so this connection has actually, this is a flat vector bundle, but with some monodromy. So because 0 is this is 0 puncture, 0 is punctured. So I'm sorry, deleted from C, and so I can trivialize C star to C star this flat bundle with connection nabla by some trivial flat connection. Sorry, I now consider universal cover and universal cover. Over the universal cover, I can trivialize with some trivial flat connection D, and I can fix. So I can choose certain trivialization here, and then I consider there is some standard way to fix this trivialization, and basically somehow looking at asymptotics of the flat sections at q equals 0, you can trivialize, and then I consider the image of the unit section on the original side here, and that is a J function. This is a definition of J function. So if you remember the mirror period of the mirror, this is parallel to the, you can think of this as being parallel to the definition of the mirror period. So you have a section omega u, which is somehow which is contained in the Hn0, which is a section which is not necessarily flat with respect to Gauss-Manning connection, and Hn0 corresponds by mirror symmetry to H00, which is whose section is 1. So 1 corresponds to up to rescaling omega u. And I consider the image with respect to the somehow flat frame. So flat frame, if you think about the meaning of this period is a pairing between omega u and a certain cycle which is Gauss-Manning constant. So so somehow the component of J function somehow corresponds to the period. So period is, in some sense, if I consider the period vector, if I take a basis of cycles and consider this kind of period vector, then this vector is somehow doing this thing. So trivialize the Gauss-Manning connection and write it in some trivialized basis. So this is a meaning of the J function. So anyway, so now I would like to introduce what would be the integer component of the J function. So if let E be a vector bundle on X, and I consider some kind of Mukai vector is defined to be some gamma class and 2 pi to the degree on 2 Chern character of E, where this Chern character is a usual Chern character, and 2 pi I to the degree on 2 is a kind of Tate shift, where somehow if you have 2p component, 2p degree cohomology class, then you multiply it by 2 pi to the pth power. And this gamma class is certain cohomology class, characteristic class, defined by what? So this is so where this is some cohomology class where if I write the tangent bundle, Chern character of tangent bundle as the product of product of 1 plus delta I, So delta I are Chown roots of the tangent bundle. Then I can define the gamma class by this equality. And this is certain, this is the gamma function, and you can tell I expand at 1 because it is regular at 1. And somehow this is a certain transcendental homology class of X. So this is not the rational characteristic class in general. But this, for example, coincides with the ordinary Mukai vector in the K3 case. Then important property of this Mukai vector is that vector is that somehow I have, if I calculate the holomorphic Euler characteristic of two holomorphic vector bundles, this is so Euler form of the, this is a sum of alternating sum of X dimension. And this is equal to the integral, the pairing of the following. So -1 to the degree on 2 on V of E and V of F. So that is somehow follows from some properties of the gamma function. So it follows from the minus Z. So in complex analysis, you have this equality pi Z on sine pi Z. And this is equal to pi I Z. 1 minus e to the minus 2 pi I Z, e to the minus 2 pi Z. So because of this relationship, somehow you see here some appearance of thought class. And this thought class will explain why I get this Euler form. So this is some generalization of Mukai vector. And then the theorem is, this is a somehow integral component of the J function.
Sorry, the reason you want to use like this gamma instead of square root of top, was that because it has anything property you want for?
Yeah, for example, this is one evidence for the gamma class to be the correct one. And another reason is mirror symmetry I'm now going to explain. Yeah. So, and also another reason would be that somehow this gamma class is there is interpretation as S1 equivariant Euler class of the positive noble bundle over in the loop space of X because of the infinite product expansion of gamma function. So there is some suggestion about why this should be true, but the main reason is mirror symmetry. So mirror symmetry. So let X be, for me, mirror symmetry. Calabi-Yau complete intersection. In my paper, I also proved the non-Calabi-Yau case, but let me explain the Calabi-Yau case. This is most important. Calabi-Yau complete intersection in a toric variety. Z. Then E is a vector bundle. Pulled back from the ambient toric variety Z. But somehow I try to delete this condition, but I cannot still have this condition. And then I have the somehow E component of the J function. It is equal to a certain unintegral period of the Bachiev-Borisov mirror. So, but for the Bachiev-Borisov construction, there is some assumption for Calabi-Yau complete intersection, and also I need some additional assumption, but I omit. For the detail, please look at the paper. And so this means that I can write it as a period over some cycle corresponding to a vector bundle E of omega u certain functions. This could be somehow normalized, divided by some function fu something. And so somehow one can think of this side as being a period, which is given by a vector bundle on X. Somehow this theorem is, I think, expected by many people and conjectured. For example, physicists calculated many examples and confirms it for many examples. And also, there is more explicit conjecture by Hosono. And also, he didn't talk about gamma class and so on, but he explained what should be the integral period in terms of hypergeometric function, and also by work of Borisov Horscher. They discussed the parameterization of the GKZ solutions to the GKZ system by K group of the variety. So somehow this somehow confirms something expected. And also in the case where Z is a toric orbifold, this is, for example, weighted projective space, for example. So for toric manifold case, we use Giventau's or Liang-Liu-Yao's mirror theorem. And in the case where toric weighted projective space, for example, one can use the mirror theorem by Coates-Kolke and Li Chen. And also some orbifold case, we are working toric orbifold case mirror symmetry. And also somehow I'd like to remove this somehow pullback from Z condition, but I can only do for a very limited class of example. For example, quintic case, I can see that this is for arbitrary vector bundle, but yes.
Well, you can also expand a J according to cohomology basis, integral cohomology basis.
Yes, yes.
Are those also integral period?
No, of course not. So this has a transcendental class, so you cannot expect to be, yeah. Yes. And also in the case of Calabi-Yau hypersurface case, somehow this equality introduced certain polarized variation Hodge structures on the quantum cohomology. And anyway, so somehow the possible application of these structures is first somehow one can understand functorially the functorial Ruan's conjecture, let's say. So originally, Ruan's conjecture somehow you can analytically continue the Gromit theory, but somehow it is not clear how it is related to the geometry of the varieties. So somehow one can give certain functorial version of Brown's conjecture, where, for example, if you have a Crepin resolution, then I have, for example, this is also conjecture. It's Mackay correspondence. Of derived category of Y is of coherent sheaves on Y is derived category coherent sheaves on X. This is also conjecture in general. And then somehow using the Z structure, one can conjecture further that somehow from this I can use this Mackay vector to get certain A periods for X. And also from X, you can consider orbifold A period for X. Sorry? Thank you. Sorry, Y. This is Y. And there is an analytic continuation map. Continuation, which somehow make this diagram commutative. So analytic continuation of Gromit-Witten theory are actually induced from some derived equivalence. That is, but possibly, sorry, I should have said, there should be some, possibly there is some rescaling of homomorphic volume form. So analytic continuation plus certain rescaling. And plus rescaling. Rescaling. So this somehow gives you certain functorial way to understand Brown's conjecture. And also some in some joint work with Tom Coates, I'm studying certain modularity of the Gromit-Witten theory, which also have been predicted by physicists Akanajik, Bouchard, and Clem, and another modularity. The example here is not a complete intersection toric variety, but is a case of local P2. So for Gromit-Witten theory of local P2, Kp, the total space of the canonical bundle of P2. So in this case, what happens is if I have Kp2, then this is mirror to, actually there is some three-dimensional mirror, but there is some one-dimensional reduction of the mirror. It is mirror to a family of elliptic curves. The local P2 is family mirror to some very simple elliptic curve, family of elliptic curves, and somehow this is a base of the family of elliptic curves with parameter u, and I have three singular points of the family, u equals 0, and use some number, for, let's say in our convention minus 127. U equal infinity, and three singular points. And we have certain monodromy of, we have certain, because this is a family of elliptic curves, we have weight 1 Hodge structure, variation Hodge structures of it. And we have some monodromy, because these are singular points. The monodromy matrix are somehow like this, 1, -1, 0, 1, and 4, 3. The number is not, of course, not at all important, because this depends on the choice of basis. So certain integral basis, these have these monodromy matrices. And you can see that actually these monodromy matrices are somehow monodromy of the period, but the period, as somehow my theorem suggests, corresponds to certain K group. And actually, one can say that in this case, this monodromy comes from the autoequivalence of duality category. Corresponds to the monodromy. So, for example, the monodromy here is a tensor product by O minus 1. And monodromy here is a spherical twist by some spherical object. And monodromy here is a tensor product by some representation under Mackay correspondence. So I don't explain that. Then somehow you can notice that every matrices here, monodromy matrices here, are in monodromy group. It turns out this is isomorphic to gamma 03, which is congruent subgroup of SL2Z, ABCD, where C is 0 mod 3. And then, sorry, let me state the theorem, the final theorem. So this is some result by Nagic, Richard Glenn. Physics argument. And recently we are going to prove it on myself. That somehow if you consider the higher genus Grohitten theory and FG and higher genus Grohitten potential is a quasi-modular function for gamma 03. So this monodromy group, you can see that this is all. Thank you for your attention. Minus it? Yes, perhaps, because the determinant is not 1. Yeah, you might notice minus 1 too. Yes.
Cardial, would that be able? I mean, of course, you said this mirror, but I mean, in non-cardial case, it wouldn't have mirror, but or mirror won't be some kind of
oscillating interval.
So yeah, but would that Z structure also can the same statement can be made for general type? Or
Yeah. General type. I see. General type. I'm not sure. For funnel or semi-positive case, maybe.
Yeah. But
the general type, maybe.
You don't. So first, do you think that's correct, or it's not correct, or it's just technical version?
I don't know.